All right, so we're going to look at some linear and exponential functions here. We're going to be given one representation, and then we're going to come up with three other ones, okay? And also, as part of the directions, it says here that we want to identify the rate of change. Okay, so you and your friends go to the state fair. It costs you $5 to get into the fair and $3 each time you go on a ride. So that $5 to get into the fair, that's like our flat fee. And then the $3 for each ride would be our rate of change. All right, since that is a constant rate of change, this is a linear function. Okay, so it's linear, and it's because we have a constant rate of change, which is 3. All right, so in a table, the independent variable would be the number of rides, and the dependent variable would be the money spent. Okay. So as soon as I pay to get into the fair, I've gone on no rides yet, but I've already spent $5. Then I do my first ride, it's $3, so now I'm up to 8. 2 rides, I've spent 11. 3, spend 14. 4 rides and 5 rides, add 3 more dollars for each one, so 17 and 20. Okay. For the graph, we need to make sure that our X and Y axes match the independent, dependent variables that we labeled in our table. So our x-axis, our independent variable, is rides, and I can number that by ones. So 0, 1, 2, 3, 4, here would be 5, 6, 7, 8, 9, 10. All right, the dependent variable, the y-axis, would have to be money spent, and I need to be able to get to at least 20, just to plot the points that are in my table. So I can count over here by 2s, 2, 4, 6, 8, 10, 12, 14, 16, 18, and that top line would be 20. All right, so when I plot those, they should end up in a line, in a linear shape, because we've already mentioned that this is linear due to the constant rate of change. So 0, 5, 1, 8, 2, 11, 3 is 14, 4 is 17, and 5 gets me to 20. Now, we do not want to connect those. This would not be a continuous function because our rides have to count by 1. We can't go on a partial ride. And our money spent must count by 3s. Okay. Our equation, it doesn't say what type of equation, so we can go ahead and make both. The explicit equation, since it is linear, it's going to have to be in the form y equals mx plus b. So we would say y is equal to our constant rate of change, that was 3, times the variable x, plus my 0th term, my flat fee, my y-intercept is the 5. If you chose to make the recursive equation, then again, remember, you always have to give something to start with. So f of 0 equals 5, and then f of x would be f of x minus 1. So every new term is the result of taking the last term and adding 3. Number 2, this time we're given the table and no context. So let's kind of see what's going on in this table before we try to make up something that, a scenario that would fit it. So when my time is 1, whether that's 1 minute, 1 second, 1 year, we don't know, but time is 1, we start with 18 of something. As time goes up by 1, what happens to the amount? Well, it tripled. 18 times 3 is 54. 54 times 3 is 162. So we need to come up with something that could triple each second, each minute, each day, each year. So we might say you are infected with lice. Okay. After 1 day, there are 18 lice on your head. Each day thereafter, the number of lice triples. Okay, so my rate of change here is that the number is tripling each day. Okay, so we did have to identify the rate of change, and that is we're multiplying by 3 each day. So for me, I'm going to change this to day and lice. Okay, so let's do our graphing. We can set up our X and Y axes. Now choosing the scale this time will be very important because the dependent variable, we go up even in just in our table to over 4,000. Okay, so I believe we still have 10 boxes here. Our independent variable, for me it's days. Yours might be different. I can count by ones again there, so 2, 4, 6, 8, 10. Now, as far as choosing a scale for the dependent variable for the y-axis, which is number of lice, I know I need to get over 4,000. I've got 10 boxes to do that. So I might count by 500s. So if this is 500, here's 1,000. Here's 1,500, 2,000. 2,500, 3,000. 3,500, 4,000. 4,500. Our top box would our top line would be 5,000. So the first few are all going to be very, very close together. So after 1 day, the number of lice is only 18. That's almost down here on the x-axis. After 2 days, it's not much higher. It's at 54, but you can barely tell a difference with this scale between those 2 points. By day 3, 162, still, it shouldn't even really be halfway up that box. But by day 4, it's finally almost to the 500. Day 5, 1,458 would be very close to 1,500. And then day 6, we need to be past 4,000. We're at 4,374, so more than halfway towards that 4,500. Okay. In this one, I would say we probably should connect it because the lice do not multiply all at once. The days go by, the lice are continuing to grow, to multiply in between those days also. So we could say, here's an exponential curve, and if we continued that to the y-intercept, the y-intercept could actually be found here. Since we are tripling, if we went back to day 0, we would just divide 18 by 3 and say there were 6 lice there. So whoever infected us must have dropped 6 lice on our head. Again, equations, it doesn't say what kind, so we'll do both. The explicit equation would need to be, since it's exponential, in the form y equals a times b to the x. So that would be y equals that 0th term that we just identified is 6 times b is our multiplier, a common ratio of 3, and then to the x power. Our recursive equation would be, again, start with one of the values in the beginning, f of 0 or f of 1. So the first one I was given was time 1. I'll start with f of 1 equal 18. And then each new f of x is derived by taking the previous value, f of x minus 1, and multiplying it by 3. Okay, now we're going to make recursive and explicit equations for each geometric sequence. So we already know going in that each of these is geometric. That means we know our explicit equations are all going to take that exponential form. And we know we're always looking to be multiplying. So number 3, we're given a scenario. Marissa has saved $1,000. So I would say that's my y-intercept, my 0th term, what I start out with. She plans to withdraw half of what's remaining in the jar at the end of each month. Now, withdraw kind of sounds like subtraction, but if we're taking out half, then we're still left with half also. So think of it more as, what does she have left? So in the beginning, she had $1,000. If she takes out half of that, that means she's left with 500. If she takes out half of the 500, then she's left with 250. Half of that, she would be left with 125, and so on. So we kind of have a nice little geometric sequence here started now. So we're ready to make our 2 equations. For explicit, we would say y equals, or f of x equals, the 0th term, the 1,000, times my multiplier. Well, my multiplier, since this is decreasing by half, is I'm just chopping each number in half. My common ratio is 1/2, and then to the x power. For the recursive equation, okay, again, start with one of your early terms, so f of 0 was 1,000. And for each next value, we take the previous one, f of x minus 1, and we multiply that by 1/2. Okay, again, we don't have to decide what type of sequence we're looking at here. This number of bacteria is definitely a geometric sequence. It said that in the directions. So what did we multiply by? From 10 to 100, that's multiplying by 10. 100 to 1,000 times 10. Now we do not have the 0th term here in our table. We know we're going to need that for the explicit equation. So let's go ahead and identify that now. If I jump back to day 0, then I need to divide these 10 bacteria by my multiplier of 10. 10 divided by 10 means I had 1 bacteria on day 0. So explicit equation, y equals 1 times 10 to the x value. Now this 1 you do not have to write down, because if there's no number in front of the common ratio, it's automatically assumed to be 1. For the recursive, f of 1 was 10, so f of 1 is 10. To get each new term, f of x, we go back to our last one, f of x minus 1, and we multiply it by 10. Number 5, this time we're multiplying our number of rectangles by 2. 2 times 2 is 4, 4 times 2 is 8. So our explicit equation would be f of x, or y, is equal to the 0th term, which is 1, times our multiplier is 2 to the x power. And again, you do not have to include the 1. Recursive, we would want f of, the first one we're given was the 0 fold, so f of 0 equals 1, and then each new one, f of x, would be equal to f of x minus 1 times 2. Number 6. Again, this one might be one that you had to really think about, work on if you weren't told that it was a geometric sequence. But we know that, so all we need to identify is a common ratio. Well, if it's not something obvious to you, start at the back with 16. You know this is geometric, so divide by the previous term. 16 divided by 64 is 1/4. If we kept going, 64 divided by 256 is 1/4. And 256 divided by 1024 is also 1/4. Okay, so my common ratio is the 1/4. All right, if this is my first, second, third, and fourth terms, then I do not yet have the 0th term. So to work backwards, rather than multiplying by 1/4, I would need to divide by 1/4, which technically dividing by 1/4 is, this is 1024 over 1. We change that into multiplication by the reciprocal, so times 4 over 1. So 1024 times 4 is 4,096. Right? That's 4,096. That's my 0th term, my y-intercept. So explicit equation would be y equals that number we just found, 4,096, times the multiplier, the common ratio was 1/4, to the x power. For recursive, first one we were given was f of 1 was 1,024, and then we derive each new term by doing 1/4 times the previous term. Notice this time I wrote the multiply by 1/4 in front. That doesn't matter. I just wanted to change it up so it wouldn't bother you if you saw that somewhere. Remember, the order of multiplication doesn't matter, so you put times 1/4 in front or in the back. They're both correct. They mean the same thing. Okay, last one. First term, second, third, and fourth. This time we are multiplying by 3. So in order to jump back here and find the 0th one, 3 divided by 3 would be 1. All right, making our explicit equation. F of x is equal to the 0th term, the 1, times our multiplier 3 to the x. Again, like always, if the 0th term is 1 in an exponential, you do not need to write it. Recursive, our first one we were given was f of 1 is 3. And then f of x would be found by taking the previous term and multiplying it by 3.